Hi guys, this video will conclude the transportation problem. We've stopped at a special case of transportation problem, the time minimizing transportation problem. As I stated in the lecture, there is a special case of transportation problems where the objective is to minimize the transportation time, like when you transport the perishable goods which have the certain time to be delivered and then they perish. This problem is the same as the transportation problem of minimizing the cost, except that the unit transportation cost is replaced by the time. So the objective function becomes maximum of transportation time is to be brought to the minimum. Unfortunately, we've got the bad news here. This is not a linear problem. But the good news is that this kind of problem can be solved iteratively using a linear programming technique, the same linear programming technique we've been using before since the beginning. We just need to repeat these simple two steps. Find a solution that provides for delivering goods from supply to demand while minimizing overall time, then find the longest transportation time. As we found the longest transportation time, we cross out all the transportation times from the solution that are greater than or equal to the longest time in the solution mix and go to step 1. Again, we find a solution that provides for delivering goods from supply to demand while minimizing overall time, then find the longest transportation time. And again, cross out this time. Now, how does this work? In the lecture there was an example. There was a matrix listing all these origins and all these destinations with a transportation duration times specified as the elements of the matrix. The whole supply, total supply at every origin was specified here. Total demand at every origin was specified here. Now, we find a solution. For example, a solution looks like this. We've got 15 units of goods to be transported from origin 1 to destination 1, 20 units of goods to be transported from origin 1 to destination 2, 2 units of goods from origin 1 to destination 3. Actually, in addition to this, we've got 13 units of goods transported from origin 2 to destination 3 to meet the total demand here. And so these are the solutions. These are the quantities to be transported. Now we look for the longest transportation time, which are represented by these numbers highlighted by bold numbers. The maximum transportation time is 45 here, is 45. So we cross out all these 45s and times which are greater than 45, which is actually 50, for example. So we cross out all the time transportation times which are equal or greater than these 45s. So we cross them out and find the solution again and find the solution again. Now we can see that solution has slightly changed. There is no these 45 minutes in the solution. The transportation of goods has been redistributed from origins to destinations. Now the shortest time is 40 minutes. We try to cross it out and repeat the solution. It turns out that there is no solution, no satisfactory solution when we cross out all the 40s. So this solution cannot be improved, so it turns to be optimal. Now how it's done technically using the Excel spreadsheet. Now we've got this example. Again, this is the matrix representing the transportation times instead of transportation costs. Again, total supplies are given here at every origin. Total demand at every destination is given here. we reserve some times some cells for the transportation plan. We set up the objective function, but in addition to the previous case, we introduce two auxiliary matrices. Instead of multiplying this range by these costs or these times, we introduce two additional auxiliary matrices. This is the first one, and this is the second one. Auxiliary matrix is actually a sum of our initial transportation duration matrix plus some mask. Using this mask, we'll be crossing out some elements of this matrix. We'll be crossing out the elements. To make it simpler, I've just introduced this every element of the auxiliary matrix as a sum. Initial matrix, cell of initial transportation duration matrix, plus the corresponding cell of the mask. So we can see that every single cell in the auxiliary matrix is equal to the sum of the initial transportation matrix and the mask, the cell from the mask. So all these are corresponding sums. Now we set up the objective function. Objective function using this auxiliary matrix, which is the sum of our initial transportation matrix plus mask, and the range representing the cells reserved for the transportation plan, which we want to optimize. We set up the objective function, we set up the constraints, all the formulas for the constraints. So the first constraint here is that the sum of these elements should be less or equal than total supply. So we set up this summation. This element will be representing the matrix, the formula for summing up these elements. The second formula is just sum of the elements in the second row, and as a constraint it will be less or equal than this particular supply at the second origin. So we repeat these formulas at these cells. Now we do the same with the demand. Actually, we need that the demand would be greater or equal than this particular value. So we set up all these summations for these cells, which are just sums of the corresponding columns in the transportation plan matrix. So now we all set. We go to the data tab, we set up the constraints, we set up the variables. This is the range representing these particular variables. We introduce the constraints. The demand should be greater, the supply at every origin should be greater, less or equal than total supply at the origin. Total demand at every destination should be met, should be satisfied, so it should be greater or equal than total demand at the destination. So we find a solution. This is our first result of this is the result of our first step, first iteration. Now we need to analyze it a little bit. So we see that what we need to find the longest transportation time in this transportation plan. So we see that 5, let's say, hours is represented. 6 hours is represented in transportation plan. 10 hours, 9 hours, 10 hours, 7 hours are not represented in the transportation plan. Again, 8 hours, 1 hour, 2 hours are represented. Then 2 hours, 5 hours, 1 hour is represented. So we can apply the mask. This mask will just put some numbers, like ridiculously high long transportation times, like 100. So we need to cross out these 10, 9, and 7. So we cross them out just by printing these ridiculously high numbers, long transportation times, 100 and 100. Now we see that the longest transportation time represented here is 8. See, 8 hours. So we can cross out everything and up to the 8. Up to the 8. So we cross out 8. And immediately as we put this mask, we can see that these values are actually getting crossed out. They're becoming so ridiculously high so that they will not be represented in the solution mix, or should not be represented in the solution mix when we get the optimal solution. So we may cross out this 9. Again, 100. This 9 is getting crossed out, and we may cross out this 8. So we see that these elements have been crossed out. 10, 8, 9, 8. Now we repeat the solution. Again, we go to the objective function, click on find a solution. We get different solution. Again, we analyze this solution. The longest transportation time now is 6, which is here. 5, this is 1, this is 2, this is 5, this is 2, this is 1. So the longest transportation time is 6. Let's try to cross out this 6. We've got 2 6s, one here and one here. So we cross out these 6s. We cross out these 6s. So we see that this 6 hours transportation duration has been crossed out. Again, we find a solution once again. Let's analyze it. We see that even with this ridiculously high transportation duration of 106 hours, it's still represented in the solution mix. Which means that we need to make a step back. Put this 6 back into the solution mix. We make a step back and find another solution. Okay, this is our solution. This is the optimal transportation plan. The quantity of goods to be transported from origin 1 to destination 1, from origin 1 to destination 2, from origin 2 to destination 2, from origin 3 to destination 2, from origin 4 to destination 1, from origin 3 to destination 3, and so forth. So this is our optimal transportation plan. We see that the longest transportation time is 6. So we may put the answer here. The longest transportation time is 6. So this is it. This is our solution. This is how we reduced the non-linear transportation problem, the time minimizing transportation problem. We turned it into a sequence of linear time of linear of linear problems into a sequence of linear problems. Thanks for watching. Until next time.